Welcome everyone and good morning to our final recap video of the semester. As I was going over your participation survey results, I found overwhelmingly people kind of fell into one of two categories, it seemed. Certainly there are a few stragglers here and there, but typically it was either people wanted to see more U substitution problems. So these ones right here, these first three examples are all going to be U substitution problems, or people wanted to see area between curves. So the next three right here, well, example 4, I guess, has 2 kind of in it, and then example 5, these are going to be areas between curves and how we calculate those out. So that's going to be the topics for my final recap video here. In fact, I think I am going to split this into a couple videos. I found that the processing speed and everything was a little bit faster last time when I split this into a few pieces. So actually in this video here, I'm going to do examples 1, 2, and 3 about U substitution, and then I'll do another video here about examples 4 and 5, the areas between curves. So without further ado, let's go ahead and get started with example number 1. We have a nice continuous function, and we have a little bit of information about it, right? It's a fairly mysterious function. However, we know on the interval from 0 to 9, if you were to try to calculate out the area under the curve, remember that's the same thing as this definite integral here. So the area under this curve, for our function on the interval from 0 to 9, that this area would be a nice positive 4. And so the question is, how can we use this to determine something about this? So the area under a slightly different function, x times f of x squared on the interval from 0 to 3. And the answer is going to be, well, we need to use U substitution here. So if we can use U substitution, we can actually see how this comes into play. So I'm going to go ahead and let u be equal to x squared. Remember, a good rule of thumb is letting u, this variable here, be your inside function. So whatever's kind of, if it's inside another piece, I would try letting that be your u. So in this case, the fact that x squared here is inside of my f function, right? It's not just f of x, but it's f of x squared. That's why I'm looking at that to try to be my u. You'll also see that when you take the derivative of this, so when I calculate out my du, we get 2x dx. And this is another thing that kind of tells you that you're on the right path, is if you see kind of this x dx, so whatever is kind of, it's part of your du, and kind of you have to ignore the constants here, right? So I don't care that I'm missing this 2. I can go ahead and rearrange that bit, not so hard. But the fact that I have both the x and the dx kind of hanging around in my equation, that kind of tells me that I'm on the good path. So let's go ahead and do that rearranging and see that I can trade in x dx for it looks like half of a du. So now we can go ahead and start swapping all of this stuff in. So again, we're trying to calculate out this here. So I'm going to do the integral from, well, okay, we'll figure out my bounds here in a second. It looks like I'm trading in the x dx for half of a du. And then we have f of x squared. But again, remember, x squared, that's the same thing as my u. So this is going to be f of u. It looks like we have half of that. And then we need to figure out the bounds. And I'm really hoping that when we change this, that I can actually use the fact that this is from 0 to 9. So in order to change the bounds, remember, this is kind of what we went over in the definite integral portions. There's a couple of different ways. But in this case, right, we need to make sure that we're switching from x bounds. So this is really, x equals 0 and x equals 3. And we need to make sure that we have u bounds, because this is now du. We're integrating with respect to u. So kind of the fact here that this was dx, we had to have x bounds. When you have du, you have to have u bounds. So we need to figure out, well, how can I change x equals 0 and x equals 3 into u bounds? Right? Well, we have this great kind of transfer rate here. We have u equals x squared. So we're going to be able to use this to go ahead and figure out how can I trade these in for u bounds. So u equals and u equals, and I'm just going to plug in, for instance, 0 for x. And when I take that and I square it, I get u equals 0. So okay, I'm going to exchange this for my u bound, which happens to be the exact same. When I go ahead and I look at x equals 3, so I say x equals 3, what does that exchange into from our u bounds? Well, I need to square it, so that way I get 9. And there we go. So we can go ahead and write this, factoring out this 1/2 bit, the integral from 0 to 9 of f of u du. I know in previous semesters, some students have gotten really hung up on this fact that kind of we don't have x here, right? That this is all x's and this is all u's. But when you remember what is the physical meaning of this, right? It's the area under the curve on this interval from 0 to 9. So this one says that the area under the curve on the interval from 0 to 9 is 4. And this down here talks about the area under the curve on the interval from 0 to 9. So that right there is 4. So this is going to be 1/2 times 4. My final answer here is going to be 2. Notice that when I did all of this, right, this is a multiple choice problem, but I really wasn't looking at the choices, right? I was kind of just solving it as if it was a standard response style question. I got out the answer 2, so now I'm going to go back here and circle my final result. But in this case, right, the answers didn't really help me guess or, eliminate any of these or whatnot, so I pretty much just ignored them until I had my final result. All right, one problem down. Let's do another 2 in this video here. Here's one I'd like to go ahead and evaluate out this indefinite integral, sine cubed of 2x and cosine of 2x. Now there is a longer way to do this, and there's a shorter way to do this, right? So the longer way actually is with using U substitution twice. And so you can do that, and it's perhaps a little bit more straightforward, but again, it takes longer. I'd like to show you the faster way to do this, especially because you've tackled a few of these problems here. And the big thing is that in order to do this faster way, we need to recognize that sine cubed, this is notation. It literally means sine of 2x, and we take that and we cube it. And this is important because, right, I told you this rule of thumb, which is when you're trying to figure out what should your u be, for your U substitution, you should choose an inside function. And so if you chose like the innermost, the inside function, I'd probably say that it's 2x. And this ends up being the longer way, and you have to do U substitution twice. In this case, if we go ahead and we select sine of 2x, we only have to use U substitution once, and it all ends up being a bit faster. So I wanted to rewrite it like this just to show you that sine of 2x really is inside of another function, right? So it is an inside function, so it does kind of fit this rule of thumb that I told you guys about. And so it's inside of the cubing function, right? Sine of 2x needs to be cubed. And writing it in this way, you really see that it's inside of this cubing function. And so it is an inside function, and it's consistent with that rule of thumb that I told you. The other great thing that comes out of this is that when you go ahead and you calculate out your du, well, the derivative of sine is going to be cosine. Leave the inside alone. Then we multiply by the derivative of the inside. That's going to be 2. And we can see that we have all of this cosine of 2x dx. This is perfectly lining up with what I have here for my du, so this will nicely get absorbed in my du. And so again, it looks like we're going to have half of a du, so if I go ahead and divide by 2 on both sides, is what I can exchange for cosine of x dx. So let's go ahead and do that. We'll do the exchange. So this is going to be 1/2 du. And then again, sine of 2x, that was my u over here. So this is going to be u cubed. And now we've simplified it down quite significantly. So again, maybe let me go ahead and factor out this 1/2 here. And when I integrate u cubed, so I need to do the antiderivative here. Remember, we need to raise my power by 1, so it goes from 3 to 4. And then I go ahead and I multiply by the reciprocal of that new power. So I'm going to go ahead and multiply by a 4th here. And let's go ahead and double check. If you were to take the derivative, the 4 would come down and reduce your power by 1. Yeah, it seems to match up. So this is the correct antiderivative. And the way that I check that is by taking the derivative, right? And making sure that I get back to where I started. All right, well, whenever we do the antiderivative, right, for one of these indefinite integrals, we need plus a constant of integration. So I'm going to do a plus c here. And then the last thing is that, right, u is something that we created. Our original problem was all in x's, so we need to go ahead and transform it back to x's. So I'm going to write here 1/8. And instead of u to the 4th, I'm going to go back and say, okay, again, my u was sine of 2x. So I'm going to go ahead and do sine of 2x. Again, all of this is being raised now to the 4th power plus my constant of integration. So this right here would be my final answer. And again, you can double check, right? If you take the derivative of this, you should get back to where we started. All right, that's my second example about a nice U substitution and kind of this fact that, right, again, there's a bit faster way to do it if you do sine of 2x, but certainly you can do it the longer way, but you have to use U substitution twice. All right, lastly, let's go ahead here and see. In fact, if you haven't done a problem like this, I recommend that you pause the video and try this one on your own here, and then when you're ready, go ahead and unpause it and we'll go over it together. All right, so I have kind of two proposed ideas here. One of them ends up going in kind of in the wrong direction and one ends up going in the right direction. I chose this problem because it's, on the more difficult side, right? I wanted to ramp up the difficulty here a bit. And the problem with this one is that there really is two inside functions, right? So first of all, cosine is inside of the squaring function. And then this 1 plus tangent is inside of the square root function. So when you're trying to figure out what your u is, right, it's not clear maybe what you should choose, especially not initially. So I went ahead and I tried one of the things, right? And that's the big story here is that really, even if you have multiple inside functions, right, you just need to try something, realize when it's not working, and then back up and try something else. But sometimes, I've seen students get more or less paralyzed, when they don't know which one to choose and they don't try anything. So the big story here is to make sure you just try something and then realize if it's not working and back up and just try something else. So I'm going to go ahead and try this cosine of t, right? So if I try u equals cosine of t, maybe starting off as potentially for my good u substitution, I take the derivative, so I calculate out du, and that gives me negative sine of t dt. And so, okay, I'm going through here. I mean, I definitely see there's the dt, but I'm looking, okay, how can I get a negative sign, right? Because I need to swap this in because I need my du's. I need to be integrating with respect to u. And so, okay, but sadly, the only thing that I have left over, especially once I substitute in for the cosine here, that's going to be u squared. But I mean, that square root of 1 plus tangent of t, I mean, I'm really seeing no way to write that as a negative sign or to get a negative sign out of this. And so I'm pretty much stuck at this point that I'll be able to transform some of the stuff if I wanted to do, maybe one line more, just to show you kind of what it looks like. I could have 1 divided by u squared. I would have 1 plus tangent of t. And then I guess I could go ahead and take this and I could make this du over negative sine of t. That's equal to dt. And so instead of dt here, I could go ahead and swap that in. And so I'd get du divided by negative sine of t. But remember, in order to evaluate out this integral, right, you need all u's. You're not allowed to have any more t's. You need to switch everything over. And so the problem is, right, how do I switch tangent and how do I switch negative sine? And remember, I have to swap them in for u's, which is equal to cosine. And so that's why this is quite difficult. And so in this case, I just say, well, maybe I shouldn't have chosen, u equals cosine. So I just back it up a little bit. Let me actually, I want to erase here. I just wanted to leave some of that stuff. I'm having a hard time erasing just the highlighted bit. All right, so I'll have to go back here. I just scoot. All right, cosine of t. That's a dt there. All right. All right, so I get something like this, kind of back to where I was here. And now let's go and try a different path. So the other thing that was inside of a function, in this case, the square root function, was this 1 plus tangent of t. And so if I go ahead and I try that to be my u, well, when I take the derivative of 1, I get 0. And when I take the derivative of tangent, I get secant squared. This is one of those that you have to memorize. So secant squared, okay, and we say, is there any way to make that look like, right, I have this like cosine squared here in the denominator. And we have to remember, well, that's exactly what secant is, right? Secant is literally 1 over cosine. So instead of secant squared, I can write 1 over cosine squared. And so now we see that we can trade in this dt and 1 over cosine squared here for my du. So that is supposed to be equal to my du. So now we're making some good progress. So let's continue on this path here. I'm going to write this as the integral, And again, I'm trading in that 1 over cosine squared dt in for du. So I'm going to go ahead and trade that in. And then again, we have 1 over, and we have the square root of 1 plus tangent, but that's exactly my u. So we get something like this inside of the square root function. Excellent. So now we've simplified it down, quite a bit, and it has all u's, right? I have u's and I have du, so I'm integrating with respect to u. So now we can go ahead and proceed with this. In order to evaluate this, right, I am going to use the power rule for antiderivatives, but I need to rewrite this. Right? The fact that I have the square root here, this means it's going to be raised to the 1/2 power, but it's in the denominator, right? So remember, this shows up as a negative exponent. So when it's in the denominator, this is a negative exponent. So now I can go ahead and apply my power rule. Remember, we need to add 1 to our exponent. So we go from negative 1/2 to positive 1/2. And then I go ahead and I multiply by the reciprocal of my new exponent here. So I'll multiply by the reciprocal, that's going to be 2. Plus a constant of integration. And you can double check, right? If I take the derivative of this, I need to get kind of back to where I started. And it does work out. So that is the correct antiderivative. Now the last thing here is that, well, u is something we constructed. So let's go ahead and kind of transform this back into t's. That's what was originally given to us. So instead of u, I'm going to write 1 plus tangent of t. This is raised to the 1/2 power. Or if you'd like to, you can use the square root. But this is going to be my final answer. And again, if you go ahead and you take the derivative of this, you should get back to where we started, and that would be a nice way to confirm that this is the correct antiderivative. All right, well, that is it for the U substitution. I hope you guys enjoyed this. Again, my second video here is going to be about areas between curves. So if you're interested in watching, you don't have to do it all, but maybe watch a couple of them or so, and just make sure that you're familiar and comfortable with these tasks. All right, guys, well, good luck tonight, and I'll see you out there.